we're going to have a methyl group, and the rest of the protein is going to be 230. So we have isolated methyl groups, and we'll talk about relaxation of zero quantum coherence. Double quantum coherence is more or less the same.
We moved it to focus what next space. Set it to time so it can change.
So then we would imagine, for example, if we call carbon S plus, and then we would have potentially being incoherent because all three protons are going to contribute. And then if we think about one of them, really I mean by this that, for example, I would have here I2 alpha plus I2 beta, I3 alpha plus I3 beta. And if I multiply all of this out, then you see for this term, I have phase line I2 alpha, I3 alpha plus I2 alpha, I3 beta plus I2 beta, I3 alpha plus I2 beta, I3 beta. So if there's no coupling for the zero quantum operator between the carbon and the hydrogen. And then what is this going to mean for what you think? Right, but two of them are degenerate. Yeah, those two are identical. So we expect a 1-2-1 triplet as opposed to if we just had the single quantum coherence, the carbon, you expect to see a quartet. Yeah. But here we just see a triplet, and then maybe this is alpha alpha, this is beta beta, alpha beta plus beta alpha. And something that is quite important then is if we ignore chemical shift, that's not going to affect relaxation, right? This is zero frequency, and then this is QJ if we're talking about hertz. This one right minus QJ. And we're going to focus on this one. And then you can work out on your own that these relax quickly. So if you're expecting a 1-2-1 triplet, if you take a small molecule, like say just alanine with the label methyl and run, let's say HMQC, you see a 1-3-1 triplet. But if you do the same thing for mannose binding protein at 80 kilodalton, you just see the center line basically. Maybe a little glimpse for the outer lines because they're so broad, they relax away. So we're going to show that this line is narrow, and then you can figure out that well by the same approach that these outer lines are broad. That's the cozy effect. Now, what are the Hamiltonians here? So if we just if we ignore chemical shift anisotropy, which is relatively small for methyl group, then what's the Hamiltonian of interest? Well, we have the dipole Hamiltonian between the carbon and H1 and between the carbon and H2, the carbon and H3, between H1 and 2, between H1 and 3, between H1 and 2, 3. Did I get them all? 2, 1, 3. 2, 3. Yeah. So we have to take into account then all of these Hamiltonians and figure out what the relaxation effects are. It'll turn out to be, we'll treat these and then treat these second. And the important thing about the methyl groups, of course, is here, if I wrote this kind of properly, and I might have written this as in organic chemistry notation, these three have different orientations. And similarly, if I look down from the top, I have H, 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 C in the middle, and then the dipole-dipole vectors also have different orientations in the lab frame. But the important thing about the methyl group is it's rotating very fast. And we assume that the methyl group is rotating fast enough to average the three Hamiltonians to a single Hamiltonian. And it's easiest to see here that if all three of these are rotating very rapidly around the symmetry axis, then the only important term is going to be the projection out of the symmetry axis. And in that limit, all three of these Hamiltonians, we can assume have the same reference axis. When we talked about the NH, Rosie, I mentioned at the end, but really we have to take into account the fact that the two Hamiltonians don't point in the same direction. Here, all three of these we're going to assume point in the same direction because the parts that are orthogonal to the symmetry axis just average away too quickly. And the same thing here will be averaging here as well. And if we work this all out, this ends up that these are scaled by another y20, another spherical quadrant. But the geometry then turns out to be critical. With all three of these, all of these three, and all of these three have these have the same reference orientation. These end up with the same orientation.
Does it matter if the motion is fixed cycle or a diffusion?
No, as long as it's fast. Is that completely true? I think that's right.
Okay.
So now we can go back. And of course, the really interesting thing about this experiment is since the effects are all going to be just due to the dipole-dipole coupling, the Troisi effect is independent of the field. Unlike the AMI dipole CSA, we have to go to the right size magnet. Here, the Troisi effect is always there. These are all things I said. So here is a potential operator. Here I wrote it as Sx, Ix. Maybe I switched the zero quantum later. So again, here's the inner resonance line of the triplet. Here are the two outer lines of the triplet. So then I did simplify to zero quantum. So I have three terms, right? One in which hydrogen 1 is in the I minus state, one in which H2 is in the minus state, and one in which H3 is in the minus state. So we have to add them all up together. And here is the complete zero quantum term, S plus I minus, S minus I plus. And here's the inner lines. And then if we fiddle around for a while, we can write this part in parentheses as 1/2 of 1 minus 4 I2Z, I3Z. Again, just using the identity that IZ is I alpha minus I beta, and the identity is I alpha plus I beta. And then we can permute the indices to get all the other terms. So part of the problem is just all the bookkeeping of all of these terms. So here's the dipole Hamiltonian. And here's the spherical harmonic that's responsible for the averaging. So this is the part that projects onto the symmetry axis. And again, the adiabatic part just is the part with the Z operators. Then I might have gotten ahead of myself. I've gotten ahead of myself. So here's the laboratory frame. So what I call theta here would, for example, be the angle between this CH vector and the lab frame. And then I want to transform to the frame of the symmetry axis. But of course, relaxation is in the lab frame, not in the molecular frame. I got ahead of myself. So then, of course, we transform from the molecular frame, where our z-axis is along the symmetry axis, to the laboratory frame by using these Wigner rotation matrices that reflect the Euler angles between the two frames. Turns out the angle between the methyl group and the methyl hydrogen bond and the symmetry axis is 70.5 degrees, and then that's fixed. But phi of t is the rotation around the symmetry axis, and that's obviously time dependent. So then if rotation is fast, all the terms that depend on phi of t will average to 0. And there's where you can ask yourself, if it was a 3-site hop, do the average 120-degree jumps average to 0 for equal populations? I think they do. And if that's the case, then this summation that went over q equals -2 to 2 collapses to just the 0th term. All the terms that depend on phi or phi of times 2 or phi times -2, those all average to 0. So we just end up with this expression that scales down by the polar angle. We just have the projection onto the symmetry axis. So now this becomes reduced Hamiltonian, in which we now have the time dependence of the symmetry axis and the scalar. But again, now, because of this averaging, all of the variables have the same coordinate system. We've only kept the part that projects on the symmetry axis. And then we would do the same thing for the HH Hamiltonian, except the angle is now 90 degrees. If this is our z-axis, then the z-axis is coming out of the board. Each of these are in the transverse plane, so that's 90 degrees relative to our z-axis. So the same argument, we just have different angles. It turns out, though, for the hydrogens, we have to worry about the flip-flop terms, because if we take one hydrogen from alpha to beta and the other one from beta to alpha, that's a zero energy process. So that also survives in this case. It doesn't for the carbon-hydrogen interaction, because of course the energies are different. Flipping a hydrogen has a different energy than flipping the carbon. So those then are still terms that are high. They're not the adiabatic terms, that are the high frequency terms. And for a large molecule, we can ignore those, as we've said before, for our adiabatic terms. So there we have to keep these flip-flop terms. So here are the flip-flop terms from the dipole Hamiltonian. And again, they get scaled. All right, so then we need to know what happens with fluctuations then for each of these Hamiltonians, right? We have to calculate the variance times the correlation time. So first, B1 commutes with the dipole coupling between the carbon and that hydrogen. That's just our old argument that the multiple quantum terms are unaffected by the dipole interaction because the levels shift up or they shift down together. That part's easy. That just says what we did. But then we have the coupling between, say, the carbon and the second hydrogen and the carbon and the third hydrogen. So here is the Hamiltonian. And again, the key part is I can write these with the same angular parts. The two Hamiltonians have the same angular components because of this fast averaging. So I'm just doing some algebra. I factored out the SZ and I replaced the I2Z and the I3Z, again, with their terms in terms of pluses and minuses. Multiply this all out. And I ended up then expressing this summed Hamiltonian as the dipole coupling constant, these angular factors, and then this term in brackets. So what's interesting about the term in brackets? Pardon?
It's everything but the zero,
It's everything
except the zero.
except the middle line of the zero quantum transition. right? It has the alpha alpha part and the beta beta part. So it's telling us about that there are fluctuations between alpha alpha and beta beta, but there aren't any fluctuation. The zero climate transition. So then this all commutes with beta 1. And if it commutes with beta 1, the double commutator commutes. Because once one commutator is 0, we can't suddenly get a non-zero commutator back. So there's no relaxation caused by that interaction on the middle line. Of course, there'll be a large contribution for these two lines. The outer lines are going to have a contribution to relaxation, but the inner lines don't.
I have a clarification
Mhm.
question. So on the graph where it's from 2J to negative 2J, the 2 hour ones are the ones that have the contribution.
Okay, so it's pretty remarkable. The middle line is completely independent. The dipole coupling, as long as this fast rotation is fast enough. And then we have to do the same thing with the HH Hamiltonian. And again, I do the exact same thing, and I find out that these also contain only terms for the outer lines. And then we have the flip-flop terms. So there's the flip-flop Hamiltonian. It acts on the 2 hydrogens, and these don't commute with these operators. So something goes on, and there's going to be both auto and cross relaxation effects, because as you can see from the triangle, as the molecule tumbles, the vectors tumble together. So there can be relaxation interference as well as auto relaxation. So we have to take all of that into account. And here, this doesn't fit our adiabatic picture. Here we have to actually go to the Redfield equations to calculate what these relaxation rates are by calculating the double commutators, et cetera. It's not as simple as our adiabatic approach. But we can sidestep all of this, because we actually don't care what the magnitude of these calculations are, as long as the center line stays narrow. And it turns out we can think about this in the same way that we talked about the Solomon equations for analyzing T1 relaxation. So we have energy conserving transitions. So here are the 3 hydrogens. The carbon isn't affected here. This is the, go back here. These flip-flop terms are only hydrogens. So what's going on with the carbon is irrelevant. So for 3 hydrogens, here is the energy levels. And these states right here are all degenerate. And here, for example, these coherences between I1 minus, I1 goes from alpha to beta, and here I2 stays alpha, I3 stays alpha, so that's this term. And over here, we have I1 is minus, and I2 is beta, I3 is alpha. So these two wavy lines are this flip-flop term that we're interested in. Is that okay? I've taken this operator that I'm interested in, the operator where hydrogen 1 is in the minus state. Again, that would mean that the carbon is in the plus state, since I'm talking about zero platinum. But again, this Hamiltonian commutes with the carbon because it's only hydrogens. Anyhow, so that's that. And then if we have a flip-flop transition between spins 1 and spins 2, you can see what happens. That will flip this beta to alpha and this alpha to beta, leaving spin 3 alone. And similarly, this alpha becomes beta, this beta becomes alpha, and spin 3 stays alone. So we can draw a whole set of flip-flop rate constants between the states. So here's the flip-flop for spins 1 and 2. There would also obviously be flip-flops for spin 1 and 3, flip-flop for spins 2 and 3. And I could draw all those pictures. And then what do I end up with after the flip-flop? Here are the coherences that I end up with. So in fact, the flip-flop between 1 and 2 converts the operator where I1 is the lowering operator to the state where spin 2, hydrogen 2, is the lowering operator. But notice I've conserved the symmetry here. I still have a center line. So the flip-flop terms don't take me out of the center line manifolds. The flip-flop terms are just flipping between different components of the center line. If the flip-flop terms took me to the outer lines, I'd be in trouble because I already know the outer lines are broad from the other Hamiltonian, from the carbon-hydrogen. So flip-flop terms got me out here. The Troisi effect wouldn't work. But the flip-flop terms just keep you in the center line, which is also sort of a remarkable thing. So that means we could write a gain-loss equation in which the flip-flop terms destroys B1, but it transfers to B2. And then I can do that for flip-flop terms between spins 1 and 3, work out the same thing, so on and so forth. And here I have then everything that happens to spin 1 when H1 is in the lowering state. So there's 2 losses and 2 gains, just like we kind of worked out with the Solomon equations. And then I go back and do the same thing for spin 2, hydrogen 2 being in the minus state, and spin 3 being in the minus state. And I can write then this all out as a series of coupled differential equations. So B1 can flip, it loses coherence to B2 and B3, B2 loses coherence to B1 and B3. B3 loses coherence to B1 and B2. But because there's no leakage to the outer components, we're just moving coherences around between that manifold that belongs to the center line. Of course, you can see that this is a hydrogen, right? Transverse hydrogen. So this is why you have to deuterate to get the methyltrosi effect. Because of course, this hydrogen would be relaxing due to its T2 with all the other hydrogens in the vicinity. And particularly important. Sorry, the online people won't see this because I'm not going to take the time to switch. You can just listen to me. Suppose this was, say, a leucine. And then we might have a carbon here, but we have a geminal hydrogen. And if these are protonated, these are quite close by. So you have a big sink where you have geminal methyls. So there's now precursors for making the methylated samples, which these are deuterated. One of the methyls in the geminal leucine or valine is protonated, the other one is deuterated, and then the whole rest is deuterated, which isn't so hard. Because otherwise, this would lead to, we have to add another term here for leakage out to the surroundings. And again, we have no reason to think that these aren't equal to each other in my diagram, right? All the energies are the same, et cetera. There's no reason to think any one of these hydrogens is different than any others. So then our center line is the sum of the three. And it's easy to show that if I just add up these three different differential equations, the time derivative of the sum is 0, because again, we're just flip-flopping within the manifold. There's no leakage to the other transitions or to the outer world. So without calculating anything directly, we know that we're going to have conservation then of the center line. There's no relaxation from the flip-flop terms. And then we can go back and do it for the pluses, where we have S minus I plus. And the same argument says that the time derivative of the B pluses is also 0. And then we know from the secular approximation that B plus and B minus don't cross-relax, so we're done. We've taken into account the all the possible Hamiltonians, ignoring any leakage. And it says then that the center line, this triplet, has no dipole relaxation. The only relaxation, the small CSA, leakage to the outside because there's never 0 protons. And I don't think it's a very big effect in large molecules. In small molecules, there's something called spin rotation of the methyl group that I think could contribute. So what are the key points? The rapid rotation of the methyl group means we reduce the different dipole Hamiltonians to a common reference frame. One reference frame for the CH dipole interactions, another reference frame for the HH interactions. The adiabatic parts of the dipole Hamiltonian between carbon and hydrogen commute with the central resonance of the multiplet. And therefore, don't contribute to relaxation. The third is that the flip-flop terms, because they're degenerate, don't lead to leakage to other transitions. They just flip-flop coherence around within the manifold that belongs with the central multiplet component. So the quote unquote auto relaxation terms are exactly balanced by the relaxation interference terms. So those don't contribute. I should have a picture but I don't. Probably bring it up. So this, of course, was discovered by Lewis K. Yep.
This means that for big enough molecule, the outer multiplet lines will just broaden out.
That's right.
So I don't have to even closely select. Like I can
That's
do
right.
an HNQC and it show me.
Yep, absolutely. And here, there should be. Awesome. Zero quantum intrusion. There's some things about the pulse sequence. Yeah, so here, in red, this is on ribonuclease H, probably at 600. So that's 155 amino acids, so about 18 kilodaltons. So, and you can see here in the zero quantum dimension, here you can see the outer lines. And red, hard to see the center line, so it's still not there. But you can see it doesn't look like a 131 triplet. The outer lines are there, but they're very much reduced. That's only 18, as I said, about 18 kilodaltons. By the time you get to 50 kilodaltons, the lines are already pretty hard to find. You can also filter them out. They're filtered out. Blue experiment. The point of the paper. But for big things, you don't have to filter them out. It's actually kind of hard to digitize enough in this dimension. I mean, it's these experiments in a moderately sized protein. The lines are so sharp that it's a real use of non-uniform sampling, just to sample far enough out to see the decay. How sharp these lines are. Of course, you go to a big thing, that's no longer a problem. The pulse sequence in the the simplest case for zero quantum, it looks a little different than the HMQC because you have to move pulses around differently. This is, I think, part of the midterm for those who haven't quite finished it yet. And, but it turns out now there's an old idea that this delay here, this tau delay, right, in the HMQC, that last delay tau is just to refocus the antiphase coherence back to in-phase coherence so that you can turn on the decoupler. And there was an old idea from Vladis Planar and Ad Bax about just start acquisition right here. Don't wait. And just turn the decoupler on after the time period tau. So the line shape is a little distorted, but you don't have relaxation during that period tau. And it turns out there was a couple of groups at the recent DNC showing that idea must date from the 80s. Now, if you use it in the Trozy scenario, in fact, it extends the size of molecules that you can get decent looking spectra quite substantially, even though it's only of order 1/125 hertz. It's only on the order of a few milliseconds, but for things approaching 200 or 300 kilodaltons, that turns out to make a surprisingly large difference in peak intensity. That's another case of an NMR old ideas coming back when Max and Planars thought this up. It was kind of cute, but wasn't really an application. And only now with the because they also didn't know about the methyltrosy back then. Only with the methyltrosy and then pushing to the largest possible systems does this turn out to be a really useful trick. Anyhow, don't ask me about the other pulse sequences. This is the most complicated pulse sequence paper we ever published. I always have to reread it to figure out what it is we did. All right, so that's methyltrosy. Yep.
So this is like the zero quantum coherence that you want to do.
Right. So if we did it for double quantum coherence, we would find the same thing.
Yeah.
And that means it's the same for things like IX, SX, which are some of those zero and double quantum. The zero quantum coherence is slightly narrower because it's a little less affected by remote hydrogens. So you never have zero remote hydrogens. So it's a little more sensitive, but not a lot. And then, oh, I should say that in one can, the big difference, of course, is whether you preserve the center line, right? The HMQC is a very old experiment, and whether you see the Trozy effect depends on whether or not you have, for example, averaged out the two outer lines. If we put a 180-degree pulse in the middle of some evolution period, this line stays where it is. These two lines get averaged together, and we end up with a center line that then is broad. So there are almost certainly papers, if one looked back in the literature, where people accidentally had this effect but didn't know it, just because they didn't have a pulse that was mixing the coherences. And same thing in the dipole-dipole CSA I think there are papers or some experiments in RNA where people realized after the fact that there was a Petrozzi effect in the sequence, but nobody recognized it at the time. It was just that the coherences weren't mixed together. So they ended up with the narrower line dominating. It's important. Whereas you could say they should have known it because they had more signal than they should. And it's actually pretty important in experiments to have some idea how much signal you expect. Because if there's, I mean, there can be lots of bad reasons why you have way too little signal, but occasionally it's a good reason. And if you have more signal than you expect, that's usually for some good reason that's worth looking at. And there's certainly people could have noticed the Petrozzi effect earlier by recognizing, yeah, this is more signal than we think. Similarly, the hydrogen bonds, scalar coupling across hydrogen bonds was recognized by Stefan Jeschek because they were running experiments in RNA, and he just thought we should have more signal. And he then paid attention to it rather than say, ask my graduate student. They paid attention to it and realized they had less signal because it was leaking across the hydrogen bond to another spin. So you should always pay attention by seeing, particularly some experiment you've never done before, you're thinking up a new experiment. Is this kind of like what I expect for signal to noise? Because you can always hope there's something new buried in the experiment, or a new molecule, new labeling scheme. There's lots of things that can be happening. Anyhow, in the absence of Hashim, we can stop early today. This is the last lecture, by the way. I will have Whitney send out an email about the final paper for people who need grades. Any questions? It's sort of astonishing that all of this balances out. It's really, really astonishing.
How could this be adapted for dynamic relaxation?
So there are, for example, CPMG experiments
Zero quantum.
that use the Petrozzi effect. There are I don't know if it's a Petrozzi readout. There are triple quantum experiments that Lewis's group has developed. I mean, originally it was double quantum, but turns out triple quantum is better for signal to noise. Triple quantum experiments measuring relaxation interference between the hydrogen dipole couplings. And particularly for larger proteins, that's a convenient way to get an estimate of the order parameter from one experiment without having a lot of different experiments. But I don't recall if then the readout after the relaxation part was the methyl Petrozzi or conventional HMTC or HSBC. Just don't remember. And if it isn't, if they haven't done it, the question is if the operator comes out of triple quantum coherence can convert that efficiently enough to the corrosion outburster to make it worthwhile. If you lose so much during relaxation during the transfer, that you don't gain, there's no point. They just don't.
But I can do CPA.
Right now, there's not, R1 row type experiments. You then have to spin lock. You have to spin lock carbon and hydrogen. But then the spin lock on the hydrogen is brewing up all of these operators. No one, to my knowledge, has figured out how to do that well. And I don't think I've seen any CEST experiment. I mean, that would have the same issues really as the R1 row.
You spin lock carbon exclusive.
Well, in here, if you could spin lock carbon and then potentially refocus with a 180. You have to do something about the transverse nitrogen. Like that. If you this would be converted to double quantum after the pulse. Affecting that, or maybe that goes with that. I'm not sure. Okay. But those are all things one has to take into account. And then, of course, suppose that worked, you would have, what you would be measuring then, because it would have averaged out the proton shift, you'd be measuring the chemical exchange effects of the single quantum carbon.
Yeah.
And then is this all worth it relative to all the existing single quantum carbon experiments?
But for a big molecule, it might be there. For a big protein.
Yeah, it is possibly. Anyhow, those are all the things one has to think about when trying to combine, the different building blocks. You have to stay away from operators that relax quickly. Sounds like next year's midterm. Other questions? Okay. You get 25 minutes of your life back to go to the 9 new experiments.